doesn't change the counter-filter solution. I should have noticed that if we transform the state linearly, then we should also, of course, transform the covariance matrix. Because, say, if you have cost function terms like x minus something transposed by covariance matrix yours by x minus something, and if we now make substitution, say x tilde is equal some linear operator like x, which comes out of here. And of course, covariance should also be transformed. So that's covariance to be replaced by m t. So when we make inverse, those terms basically cancel. So that's the first point. And when you make this scaling in NKF, you always have to think about it because your covariance is carried by the ensemble. So this happens automatically behind the scenes. But when you run the actual Kalman filter and do your scale, you need to take care of the covariance. And so the second was the question about the smoother. Actually, the answer can be quite true. So if there is some true system trajectory in time, and if we make sequential assimilation, and our estimated trajectory looks something like, say, that, it doesn't have to be improved, but in general it's improved, it becomes closer to the trajectory. And if we then run the smoother, then on general, the discrepancy between the estimated trajectory and the trajectory should reduce. Say, instead of this analysis, we may have closer to the truth solution, and etc., etc. So, in this way, if the trajectory is smooth, you can say that the smoother trajectory is smoother than the heated trajectory. Maybe this is why it's called smooth. So now, just to remind you, when we finish, we talked about advantages and disadvantages of some methods before you introducing them. And then I talked why dynamic covariance can be critically important in some applications. And now I'll talk about some conventions used throughout several lectures. Those N and P are they denote different dimensions. Fortunately, Olivier Bolograd uses the same N as me for the state size, for the state dimension, and the same P for the number of observations. So this is the same. And I will use M for the size of the ensemble. Now, as before, superscripts FA, they denote forecast analysis. And so we now have ensemble matrix P, or if we subtract the ensemble mean from it, we get ensemble anomaly matrix, which we denote A. A is for anomalies. And X here, throughout this lecture, will be ensemble mean, which is just arithmetic mean of the ensemble matrix. Y is the same symbol used for observations, and so those symbols are basically the same. And very familiar with this whole matrix issues, they note the sizes of these matrices. So you can see that observation error covariance is observation by observation. H, the observation matrix, is P by P, and Kalman gain is N by P. And T we will use later for ensemble transform matrices, and we will talk about that. So just before I proceed, it's useful to have some idea of relation between those numbers. And as we say throughout our lectures, N, which is state size, is really big. Say in operational systems, it's say 10 to the 6 up to 10 to the 9. And it's usually we have you can have lots of observations, but it's usually a few orders of magnitude smaller than that in our cycle. So we can say that N usually is still much bigger than P. And this is P, number of observations, usually is still bigger than sample size. That's total time. Right. So if you think about these matrices involved, matrix H is usually it has one row for each observation, so it's probably rather wide. That's dimension 8, but usually not very tall. So this is usually smaller than and so the ensemble matrix indeed is very thin and tall. So, for example, when we have something like HTR, so when you see something like HT, how we can imagine this is you can see it as some H matrix, some really big P matrix, and against some tall H transform matrix, something like that. So it's when you see any formulas in matrix notation, I found for myself quite useful at times to see them this way. Now, we have briefly mentioned that there are two main kinds of the ensemble Kalman filter, which in literature called stochastic and deterministic Kalman filter. The stochastic Kalman filter is also called like traditional ensemble Kalman filter or traditional NKF. So all Kalman filters, all ensemble Kalman filters, they update the ensemble mean in the same way. So there's no difference between them in this regard. What happens is the rate of ensemble mean doesn't depend on distinct one units. So the whole difference is how the schemes update the covariance. And the traditional NKF, so that's the Kalman filter analysis equation for the covariance update. And so the stochastic Kalman filter approximates this stochastically, which means this relation is true in some sense on average. When your ensemble becomes really big, it should in theory match this Kalman filter update. If it's small, it approximates its approximate. And the so-called ensemble square root filters, they exactly satisfy this. So they update the ensemble anomalies in such a way that this equation is satisfied exactly. So let's, before going into the entails just list some general properties of the stochastic of the traditional entail, which has been put up by Evans in 1994 and used up to now in some operational systems like in Canada by Hutkana and Mitchell. Some properties of the traditional entail and some properties of the square root ensemble square root filters. So the approximation error of the traditional entail allegedly is proportional to the inverse square root of the ensemble cells. That's quite common for the stochastic Monte Carlo approximations. It's also known that on average the traditional NKF tends to underestimate covariance rather than overestimate. And because of this, it has some undesirable properties, but we'll talk about this later. So if you talk about ensemble square root filters, we should know that for a linear perfect model system, the ensemble square root filter is equivalent to Kalman filter. So in what sense? In the sense that if say, we have a Kalman filter which is characterized by covariance P at some moment of time and the state estimate X. And if we now set up a matching ensemble square root filter such that this covariance is equal to ensemble normally that transpose n-1, and X is equal E1 over M. So then and run both systems forward and down, that at all with the same observations. Then at all moments of time, the covariances which we calculate from the system should and the state estimates on all 4 moments of time should match each other. So just probably should say how this works. This one, big one, is a column state vector with all elements equal by 1. Right? So when we take ensemble matrix and the length of this vector is such that it matches the matrix it's multiplied with. So in this case, it has n elements, the same as the number of ensemble members. So when we multiply this matrix there, this is a column vector with all elements. Say the first element of this column vector is just sum of every element in the first row of this ensemble matrix. So 1 over m E1 is a simple way to say that's ensemble element. Now, if our covariance T has some rank and our Kalman filter covariance P has rank n, it doesn't have to match the state size. It can be much smaller, in fact. Then, to factorize this, we need to have n plus 1 ensemble members. So if we have Kalman filter for a system with the effective model dimension of n, don't mess with the state dimension. Then we need n plus 1 ensemble members to put up the equivalent ensemble square root system. And another point is that any analysis scheme that satisfies this equation exactly with ensemble square root filter. Say, and I think probably this might be not clear to everybody, but if you, for example, say, consider C, which is one of the ensembles, if you consider any of the schemes which satisfies this equation exactly, they all classify as ensemble square root filter. And so later we'll talk about the solution space, which can be very compactly described of all possible ensemble square root filters. So whatever scheme is doing, if it satisfies this, it belongs to the ESRF solution space. So now I show you the plots which from our favorite filter rule, which shows you example of performance of the relative performance of the square root filter and the traditional NKF. So what we have here, say, on this axis is the ensemble size. And what we have on this axis is the average RMS error, final RMS error of the system, average for big number of realizations. So this very first chart was obtained with the linear regression model, which was introduced by Evenson. That's a very simple model. As introduced by Evenson, you have one-dimensional grid, so typically of 1,000 grid points. You have some profile, which can be any physical property, which propagates forward in time one grid point at one time unit. And this profile is observed for equally spaced locations at each moment of time. And they simulate observations which are observed in these locations. And there are so the observation error variance is 0.001, so that's the standard deviation of observation is 0.1, etc., etc. So that's some standard setting. And in fact, this model is equivalent to a simulated static profile, because you may see this profile as constant in time, but the actual observation conditions moving in opposite direction instead. So you know what to expect. If you simulate some static model state and have more and more observations, so eventually you should have zero error. So this thick line shows the best estimate in the least squares, the best possible RMS error in the least squares sense of the true state, which you know, with the initial ensembles. I forgot to say that in this particular ensemble, the model was set up as a sum of 51 Fourier harmonics. So the model subspace has dimension 51. So we see how the best possible mesh, the error of the best possible mesh reduces with the growing ensemble size until it goes to 0 to 51 and continues to stay 0. Then this very thin line, but continuous thin line, shows the performance of the square root filter. So it's very close to the best estimate, but it doesn't measure because this is taken after some finite number of steps, not infinite number of steps in time. So it doesn't quite measure, but it's very close. And this dotted line shows the performance of the traditional NKF. And I think I'll try now to run some experiment, which actually will show you these performances. So I'll run this in the small package which is called MKF.lab, which is available freely from our website, NERS. So this small
make the code bigger so people can see better what's happening.
So basically, I run it not from the package sort of directly. So what this is doing is I edit the path where I'm in now to the method path. So that's all things number. So each experiment is set up by each particular parameter file which I have in this directory. So I will just run one of those parameter files. Say this, they look like that. Just a second. So it's a bit. I'll try to increase the font size so you can see better what's in there. So, for example, we will use a method which is MKF. That's this key. That's our grid size. Number of observations, we reach a simulation cycle, etc., etc. Observation error variance, so it's just a simple text file. And we use no localization because the localization length is set to 0, etc., etc. So it's quite simple to change the parameters and run multiple experiments and compare how the system performs the different settings. And so I'll try to do it now. Say, if I run main, which is sort of the main call one uses when running the parameter file directly. So what you see now is this sort of diagnostic window. So we run the system for 1,000 steps. And so the main window we want to keep an eye on is this upper one. So this thick line shows how the RMS error, root mean square error, between the true solution, which we know, and the best ensemble estimate changes in time. So after some transitional period, you can see that RMS error stabilizes. It doesn't improve much. So it's probably is around somewhere, around the level 0.2. This is about the level which was reported for this ensemble size. And the ensemble size used here is ensemble size is 60. So if you look at now this plot, you don't see it's so small, but the ensemble size 60 is here. And this is probably around 0.2. That's the RMS error from this particular, that's quite close to what you see now in a single experiment. And what's this dotted line is the ensemble spread. So I will talk about it later, but in well-tuned system, in well-operating system, the ensemble spread on average should match observation error. what happens if they don't connect? If the ensemble state goes to zero, this is called ensemble collapse. So the system is suboptimal, and it is suboptimal because it uses Monte Carlo approximation of the covariance of data. So at each step, you don't have exactly the covariance you need have in the Kelvin filter framework. So the system is suboptimal. And because it's suboptimal, it's over-optimistic. It decreases its covariance much more than it should decrease after each step. And what happens when the covariance decreases too much? The system doesn't trust observations because it says, my covariance, my uncertainty is so small that I'm sure that we are in the right state now. I don't care about observations. That's what you see. The system becomes non-responsive to the observations. This whole situation is called ensemble collapse, and the traditional NKF is quite prone to this ensemble collapse because on average, as I said, it underestimates the covariance. Of course, it can be tweaked. There are many ways you can tweak any operational system. For example, you can introduce inflation here so that after each step, your covariance is a bit larger than the one which comes from the traditional NKF. And then this performance will drastically improve indeed. So you can tweak the system, but without tweaking, just running plain effects like that. So let's now compare how this the system will behave if you leave everything as is, but change the scheme. We now take the square root scheme, which is called ensemble transform Kalman filter, or ETKF.
I just have one quick question while we're on the traditional ENKF. So you mentioned that there would be a need for inflating the covariance.
For example.
And how is that inflation done? That would one just run it like is run there, and then empirically try different cycles such that the spread becomes the same as the RMS error? Would that it's just done?
That's a very good way to tune the system. So if you have in practice you almost every time if you tune systems in such a way that your ensemble spread matches the RMS error, it sort of behaves optimally. But in practice you don't know the truth. So,
right, there's no theoretical way to do it.
So you have to use what we call innovation statistics. So and I will later go how to do that. How to tune the system. So we will now run.
Excuse me.
Yes.
Sorry. This is actually here we are solving the Lorentz system.
No, that's linear regression system. It's described in Evenson, I think 2004 paper. But it's also described in our paper. It's sakov and Wolf. I think it's in monthly weather. So that's sort of assimilating static field. And because we assimilate static field, that's a very useful test. We know the expectations. So each time you have a new scheme, some new improvement, it's a good idea to test it with a number of different models, because different models, they reveal different sides of your data simulation system. So I now changed
And how do you generate the observations here?
Sorry?
How do you generate the observations?
Now generate observations. So as I said, at any moment of time, I observe the models, the true model state, which I know.
Yes. How do you know that?
Because I run twin system experiment. I run it, I know it through solution, I run it forward, and now I say, I pretend I don't know it. Okay, so I put up a data simulating system, which starts from a very wide ensemble. So we see how big the initial uncertainty is. So, and I actually run this data simulating system forward, and so I feed it with the observations, which I generated from the true solution. I add error to this observation, to each solution. to generate this observation.
And what is the dimension n for this model?
What
What is the dimension n for this model?
dimension? Right.
N.
That's 1,000 grid points. 1,000.
Sample sizing here.
It can be anything. So, but in this case, it's just 1,000. And so
And what is p?
P is the number of observations in each simulation cycle.
Is an, and what do you use? You see
So
my
for P is equal for, we probably don't see from there, so P is 4, and we use 60 members. So, as I said, the model dimension here is 51. So, now we run ensemble square root filter with 16 members. And as I said, for square root filter, if you have system of some specified dimension, you only need n plus 1 sort of members in the perfect model and linear model framework. That's what this model is. So let's look now how it will perform compared with the traditional NKR. So I run the same parameter file because I modified it. We will now use different scheme. And so you can see that after some conditional period, so this is the same but in logarithmic scale. So you can see that this frequency is much better in this graph. So after some conditional scale, conditional period, basically the ensemble spread, which is the ensemble estimate of the uncertainty of the system state, perfectly matches the RMS error. So that's how the Kalman filter should work in the linear case. That's what it's supposed to do. So another thing to note here, which sometimes is useful, it's certainly a very useful concept in practice, is the description of your ensemble or of your covariance matrix, which is the same. So I wonder how many know what the SVD decomposition is? Singular value decomposition. How many know what it is? So it's not really a concept which probably can be introduced in 1 or 2 minutes. It requires maybe another lecture to be familiar fully with. But very briefly, if you have any matrix, like for example ensemble matrix A, matrix of ensemble moments, can be decomposed as I will talk here about so-called truncated SVD decomposition. So in product of 3 other matrices, which is can be B, say L, and W. Usually people use W. So where this matrix is orthonormal, so each column is a vector which is orthogonal to all other vectors and the norm 1. But what's more important is what I'm talking here is this matrix, which is just diagonal. So it has some diagonal values with all other values equal to 0. And what these diagonal values mean is can be described as the variance in different modes which present in the ensemble. Say, if we have a number of, for example, Fourier modes, say 51, we have some variance associated with each mode. So, strictly speaking, if we make decomposition of the ensemble anomalies matrix, then these values will be square root of variance. That's standard deviations of each mode, sigma 1, so what this shows is the normalized SVD spectrum. That's the initial spectrum is shown in blue, and the final spectrum shown in green. So you may know that it became rectangular. And why is that? Because there is a theory on filtering theory that after each filtering step, after each simulation cycle, the variance of each our uncertainty in the system reduces. So the variance of each node actually reduces, but it reduces in such a way that the initially ordered sequence remains monotonic, and the actual reduction is also monotonic. So the very largest node, which carries most of all variance, uses most, etc. So if you have some initial spectrum and you have linear system, what happens in time? That the spectrum becomes flatter and smaller, and in the very end it becomes just rectangular. That's how it should behave. And if you compare this with the traditional NKF behavior, here you can see that it became rectangular, so it doesn't behave like common filter system should. So the second experiment, which is summarized in this graph, it's also not very well seen. I'm sorry for that. On this graph, it's a similar sort of performance graph of the model RMS error averaged over a long period of time, now ran with the two-dimensional Lorentz system, depending on the sample size. In the standard system which ran exactly like in the original paper by 1996 by Lorentz and Emmanuel. So this lower curve shows the performance of the ensemble square root filter, and the upper curve shows the performance of the traditional NKS system. You can see that for some rather large ensemble sizes, the performance of both systems matches. But for small ensemble sizes, the square root system behaves much better. You can also see that this performance of the square root system is sort of is not very sensitive to the ensemble size. As soon as it has enough ensemble members, it doesn't really improve and actually deteriorate. So if you compare RMS error at this point and RMS error with big ensemble size, you can see slight deterioration, and there are some reasons for that. So my point is that these square root systems, in these experiments, they don't behave like stochastic Monte Carlo systems, because for stochastic Monte Carlo system, we expect improvement in performance, like ensemble size to the inverse power of the ensemble size, on some theoretical offset. But these square root systems, they behave like when they have certain ensemble size, there's almost no further improvement in their performance. This means that in this perfect model experiments, the NKF, the deterministic NKF systems, they don't behave like stochastic system. They behave like as though this relation is not approximation, as factorization. So as soon as we're able to factorize the covariance with our ensemble anomalous matrix, the system is happy, and it means no further increase in the ensemble size. So, any questions on that?
So just a short question. If you put square roots ensemble method, that comes from the order of error 1 over the square root of n, or what is the square root?
Yeah. Okay. On my next slide, I will go to this. Why it's actually called square system? Okay. Not on the next slide, but the slides after the next. Okay. So I will now go into details how the ensemble square root filters will, and then I will consider how the traditional ensemble will work. And why start with the deterministic filters? Because there are very few cases. Actually, it's very hard to put up a case. It's impossible where traditional NKF would outperform a deterministic NKF in practice. So, as a rule of thumb, if you want to set up the NKF system, you use square root filter. Unless you have some very specific reason why you want to use traditional NKF. So, and in some cases also, conceptually, this deterministic ensemble square root filters, they are also simpler than the traditional. So, let's consider the NKF, the Kalman filter analysis step. How we update our ensemble in such a way that the implicitly carry covariance and the state estimate change according to Kalman filter update formulas. So we come to the analysis stage. The sum ensemble E, and we, as I talked about, we split it into the ensemble mean and the matrix of the ensemble anomalies. And we have the ensemble mean according to the Kalman formula for updating the mean. And so the real difference between the schemes is how we update the anomalies. And all ensemble filters can be classified in two types. I call it right multiplied, left multiplied. Sometimes in literature people call it post multiplied, pre multiplied. So that's quite arbitrary. But so what I want to say that in the right multiplied update scheme, we calculate the ensemble transform matrix T such that when we multiply the matrix of ensemble anomalies by this matrix T, the new matrix of ensemble anomalies is such that it exactly matches, honors the Kalman filter update equation for the covariance. And the same for the left multiplied filters. The only difference is in how this matrix looks like. So, in the right update fields, this is very small. This is ensemble by ensemble size. So, this is hugely tall. So, this matrix is quite a bit, and well, in the left multiplied case, this is huge. It's state by state size. So, you may say, what's the use from this matrix? Well, it's a very nice theoretical concept. So, in particular, when you want, for example, compare different polarization schemes which are done in space, you want to use experiments, let's multiply square root of filter. So, but for normal use, it's just some exotics which just exist in theory. Right. So in normal life, we all want to use right multiplied small ensemble data. Ensemble transformation. How calculative we come to this later. How much time's up? 10 minutes. 10 minutes. So continue now. Before we go into this, we need to talk a bit what's the matrix square root is. So there are two definitions in literature of the matrix square root. One is matrix B is called square root of matrix A if B by B Hermitian, which is transposed and complexly conjugated, is equal A. That's one concept. And another one is B is called the square root of A if A is equal B times B. So this sometimes they work in the same way, but generally these are different definitions. And I think it's worth to draw your attention to this, because if you use term matrix square root freely, you may run in some trouble. Say, if you have, say, a diagonal matrix, say, these two elements of one on the diagonal and two zeros elsewhere, what's the square root of such matrix is? Obviously, if you put 1, 1, that's the square root, because if you multiply this by itself, conjugated or not, transposed or not, you'll get this. Obviously, minus 1, 1, also square root. Okay? Then 1 minus 1 square root, minus 1 minus 1 is also square root of this matrix. So the matrix square root is not unique in even simplest situations. That's the point made here. But what's important to know that in mathematical literature, by a to the power 1/2, I should have put brackets here, around here, so a to the power 1/2 denotes specific unit square root of a. And specifically, if you have positive different matrix, like covariance, for example, or positive semi-definite, which is non-negative, then this notation, a to the power 1/2, denotes specific square, denotes positive definite square root of a. And if you look at these four matrices, there's only one of them, this one, which is positive definite. So it can be shown that this, if the original matrix is positive definite, and there is unique positive definite square root of this matrix. So far, both for symmetric matrices, both definitions work in the same way. But if we have non-symmetric matrix, square root can become tricky. These definitions start to work quite differently. And so how to show this? Say, if you have non-symmetric matrix, which is positive definite, then the square root, and this eigenvalue decomposition, then the unique square root can be defined like that. Well, with this definition, this square root cannot be defined at all with this definition. So the point, I guess, I want that for how it's called, for continuity of the operation of matrix square root, one should use this definition. And this one is used mainly in engineering literature. So it's quite common to use covariance to the power of 1/2 is equivalent to the matrix ensemble moments, because say divided by square root of n minus 1. Because if we use this field definition multiplied by the transpose matrix, we get AAT to the n minus 1. So you can say that the matrix of ensemble anomalies is the square root of covariance. And many people use this in example in the NKF literature. But in fact, this is not correct, because if this is holistic definite, so this because if the original matrix is symmetric, then the unique square root of this positive semi-definite matrix is also symmetric, while the ensemble matrix is tall and narrow. It's not symmetric matrix. If you make conjugation, you get a completely different shape. So but in the original formulation of square root filters, put up by Potter and by Anders in 63 and 68, these people actually used square root of covariance matrix, which is also symmetric. It's only later in literature people start to use this as a substitute for the ensemble anomalies. So from now on, I will use scale ensemble anomalies instead of A. So before this moment of time, you could write that covariance is equal to 1 n minus 1 A over T. From this moment of time on, T is equal to AT. Because we scale this ensemble anomalies by a factor of n minus 1. That's purely for simplicity of in the equations. So the next point is very short derivation of the square root field. I will probably leave it here until tomorrow, because I think it's very simple, but I want you to fully appreciate what's done here. You may be a bit touched now. So, just going ahead, if you look at the original papers where different versions of ensemble square root filters were introduced, so the paper by Bishop and others, paper by Hammer, and by Fan, and there's some by some other people, by Anderson. Each of these derivations takes several pages of journal of manuscript of the manuscript to derive the final data equation. In fact, it can be obtained just in a few lines of algebra, but I will go to this tomorrow. Let's see today. Any questions?
Just more of a comment. So it's pretty interesting that when you that there's only one unique square root matrix that is symmetric and positive definite. because you could actually take any orthonormal matrix and post-multiply that by A, and still form P out of the outer product of the matrix square root. And I think there's like an infinite number of orthonormal matrices. It's just that it's amazing to me that there's only one of that infinite number that makes it symmetric and positive
I think
definite.
that's when you read about this in matrix algebra textbooks, it's quite trivial to demonstrate. I'm not sure if I can recall how it's done, but it's just maybe one sentence. Why it is so? Why it's unique?